For thousands of years, people have looked toward the constellation Orion and noticed a star that seemed different from the others. Most stars appear steady. Night after night, year after year, their brightness changes little to the naked eye. But one reddish point of light often appeared to shift in intensity. Sometimes it shone brilliantly. At other times, it seemed noticeably fainter. Long before astronomy became a science, observers recognized that something unusual was happening. That star is Betelgeuse. Today, it remains one of the most famous stars in the sky, not only because of its brightness, but because it offers a rare opportunity to watch a giant star living through the final stages of its existence. Modern telescopes have revealed that behind its familiar glow lies a chaotic environment shaped by immense forces, violent eruptions, and constant change. Far from being a quiet celestial landmark, Betelgeuse is one of the most dynamic objects in our galactic neighborhood. Located roughly 650 light-years from Earth, Betelgeuse belongs to a category known as red supergiants. These stars begin their lives with masses many times greater than our Sun. Their enormous size allows them to generate tremendous amounts of energy, but it also causes them to consume their nuclear fuel at a remarkably fast rate. In astronomy, larger stars often live shorter lives. While stars like the Sun can remain stable for billions of years, massive stars race through their fuel supplies and evolve much more rapidly. By the time a red supergiant forms, it has already undergone dramatic internal transformations. Betelgeuse represents one of the final chapters of that process. The scale of the star is difficult to comprehend. If Betelgeuse occupied the center of our solar system, its outer atmosphere would stretch beyond the orbit of Mars. Mercury, Venus, Earth, and Mars would all be swallowed by the star's enormous outer layers. Even Jupiter would appear surprisingly close to its surface. Despite this immense size, Betelgeuse is not particularly dense. In fact, much of its vast volume consists of extremely diffuse gas. The star has expanded to such enormous proportions that its outer regions are far less compact than those found in smaller stars. Its reddish appearance comes from temperature. Although Betelgeuse is vastly more powerful than the Sun, its surface is significantly cooler. Cooler stars emit more red and orange light, giving Betelgeuse its distinctive color. Yet appearances can be deceptive. Even with a cooler surface, the star radiates tens of thousands of times more energy than the Sun. The reason is simple. Its surface area is gigantic. Imagine replacing a small light bulb with an entire glowing stadium. Even if each section shines less intensely, the total amount of light produced becomes enormous. That is essentially what happens with Betelgeuse. Deep within the star, nuclear fusion continues generating energy. But unlike younger stars, where fusion occurs in relatively stable conditions, Betelgeuse has entered a far more complicated phase of evolution. Different layers of the star are engaged in different processes simultaneously. The interior resembles a giant cosmic onion. One layer may be fusing one type of element while another layer supports a different fusion reaction entirely. These overlapping processes create a delicate balance between gravity pulling inward and energy pushing outward. Maintaining that balance becomes increasingly difficult as the star ages. The result is instability. Throughout the interior, massive currents of superheated plasma rise and fall continuously. These convection currents transport energy from deeper layers toward the surface. Calling them currents barely captures their scale. Some of these structures may be comparable in size to Earth's entire orbit around the Sun. Imagine colossal rivers of glowing gas, larger than planetary systems, endlessly circulating beneath the surface. These motions reshape the star from within, creating regions that brighten, cool, expand, and collapse over time. Betelgeuse is not a static object. It is constantly changing. One of the most dramatic reminders of this fact occurred between late 2019 and early 2020. Astronomers noticed something extraordinary. Betelgeuse began fading. Over a matter of months, its brightness dropped dramatically. To casual observers, the difference might not have seemed shocking, but for scientists who monitor stars carefully, the change immediately attracted attention. The timing was especially intriguing because Betelgeuse has long been considered a candidate for a future supernova. A supernova occurs when a massive star exhausts its fuel and undergoes catastrophic collapse. The resulting explosion can briefly outshine entire galaxies and scatter heavy elements across space. Could Betelgeuse be preparing for such an event? News headlines quickly appeared around the world. Speculation spread across social media, astronomy forums, and scientific discussions. Many people wondered whether humanity was about to witness one of the greatest astronomical spectacles in recorded history. The reality turned out to be different. As observations accumulated, researchers developed a more detailed explanation. Evidence suggested that Betelgeuse had ejected a large quantity of material from its surface. That material traveled outward and cooled. Eventually, it formed a cloud of dust that partially blocked the star's light from Earth's perspective. The star itself had not begun exploding. Instead, it had essentially hidden behind its own debris. The event became known as the Great Dimming. Far from disappointing astronomers, it provided valuable information about how red supergiants behave. For the first time, scientists could closely examine a major mass loss event as it unfolded. The observations revealed that Betelgeuse is actively shedding material into surrounding space. This process is important because stars do not simply disappear when they die. Throughout their lives, they continuously enrich their environments. Gas expelled by stars eventually mixes with interstellar clouds. Over time, those clouds can form new stars, new planets, and potentially new forms of life. In a very real sense, the material released by ancient stars becomes the building blocks of future worlds. Betelgeuse is participating in that cycle right now. Modern observatories have provided unprecedented views of these processes. Visible light observations track changes in brightness. Infrared instruments can penetrate dust clouds and reveal material that would otherwise remain hidden. High-resolution imaging has uncovered giant plumes extending outward from the star. Rather than appearing perfectly spherical, Betelgeuse often looks uneven and distorted. Different regions behave differently. Some areas release more material than others. Some brighten while others dim. Vast structures emerge and evolve across the stellar surface. These discoveries have challenged older models that portrayed red supergiants as relatively simple objects. Instead, Betelgeuse appears extraordinarily complex. Researchers are now investigating whether magnetic fields play a larger role than previously suspected. Magnetic activity may influence how energy moves through the outer atmosphere and could help explain certain patterns of variability. Others believe that interactions between pulsations, convection currents, and mass ejections create behavior that current models cannot fully reproduce. In other words, Betelgeuse is still teaching astronomers new lessons. And perhaps the most important lesson is humility. Despite centuries of observation and decades of advanced technology, scientists still cannot predict exactly when a star like Betelgeuse will explode. The star is undoubtedly approaching the final stages of its life. But approaching means something very different in astronomy. A star may appear close to death while still surviving for thousands or even tens of thousands of years. On cosmic timescales, that interval is brief. On human timescales, it is almost unimaginable. Betelgeuse could explode tomorrow. It could also remain visible for many future civilizations. Current science simply cannot determine the exact timing. What matters most is not predicting the explosion itself. What matters is understanding the journey. Massive stars like Betelgeuse are responsible for creating many of the elements that make planets and life possible. Carbon, oxygen, silicon, calcium, and many other elements essential to the universe originate inside stars. When those stars eventually die, their material returns to space. That material becomes part of future generations of stars and worlds. Every atom of oxygen you breathe was forged in the interior of a star. Every atom of calcium in your bones has a stellar origin. In that sense, stars like Betelgeuse are not merely distant objects. They are part of a cosmic story that includes us. The reason Betelgeuse continues to fascinate astronomers is not because it is dying. It is because it reveals how dynamic the universe truly is. From Earth, the night sky often appears calm and unchanging. But beneath that appearance lies constant activity. Stars expand and contract. Magnetic fields twist and reconnect. Massive clouds of plasma rise and fall. Entire stellar atmospheres drift into space. The universe is not frozen. It is evolving. And few stars demonstrate that reality more dramatically than Betelgeuse. Every new observation answers one question while raising several more. Why do some mass ejections occur when they do? How do convection currents interact with magnetic activity? What signals genuinely indicate an approaching supernova? Scientists continue searching for those answers. Meanwhile, Betelgeuse remains suspended in Orion's shoulder, glowing red against the darkness, carrying on processes of astonishing complexity hidden beneath its familiar light. Whether its final explosion occurs centuries from now or thousands of years in the future, its scientific importance is already secure. Because Betelgeuse has become more than a star. It has become one of humanity's best windows into the powerful forces that shape stellar evolution and transform the matter of the universe itself.